Zarin Chaudhary. This is my physics lab 5, following Slinky problem. Table of contents. In this lab, I'll cover 5 main things: introduction, fundamental principles, experiment, tracker, third computational model, fourth results and conclusion, and finally the error analysis. So the objective is to analyze the motion of a falling slinky, the bottom part of the slinky, using a tracker, and then create a computational model that imitates the real life motion. Then I'll compare the actual and predicted motion of the slinky. The key ideas here are Newton's second law that says force is proportional to the rate of change of momentum in a body. Second is the universal law of gravitation. Every particle of mass attracts other particles by the formula, and force is proportional to the product of masses and inversely proportional to the square of the distance between them. The system in this case is the slinky and the earth, and surroundings is everything else. So the preview results. The actual video and the computational model both demonstrated that the bottom part of the slinky remained constant until the top part came down. The graph matched well within the limits of experimental accuracy. So the fundamental principle used are Newton's second law, the velocity update and position update formulas, and Newton's universal law of gravitation, that is force of gravitation is equal to gm into j hat, where j hat is the direction vector for the negative y direction. So this is me tracking the motion of the slinky. The height of Derek Muller, whose Veritasium was used for calibration, which was 1.75 meters. The mass of the slinky was 0.204 kgs. The initial position was 0 meters and the final position was 0, minus 4.79, 0 meters. The video was shot in 300 frames per second. So this is the computational mode, computational code and the initial conditions. So the values for the mass of the slinky 0.204 kg and the initial position was put as the values found from tracker, and the initial velocity was put as 0 since the slinky starts at rest. The value of g was put as 9.8 meter per second square, and j hat is the, as said before, negative direction, the direction vector for the negative y direction, and the proportionality constant for the drag force in computational code part 2 for B was put as 103. Now this is the computational model for part 1. This was still t is equal to 1.075 seconds, which was when the top of the slinky reaches the bottom. The formula for the gravitational force was put as discussed in the fundamental principles slide. The force of tension is opposite and equal to weight, and hence the bottom part of the slinky stays constant, stationary, as Fnet till t is equal to 1.078 is 0. After that, I put the velocity and position update formulas as mentioned before. This is computational model part 2. This was the code for the model part 2, which is still t is equal to 1.629 seconds. This was the time of the last observation on tracker. The drag force is included since the slinky as a whole is moving down. Summing up this drag force and the weight, we get the net force. After that, I again put the velocity and position update formulas for the loop. The following are the graphs for the predicting motion and the actual motion of the slinky. We can see the computational model mimics the actual motion well. It deviates a bit away in the middle. In the beginning, the model predicts the motion well since the slinky was stationary and the Fnet was 0. Error analysis: there were a few discrepancies between the predicted and the actual motion. This may be due to the human error since the slinky was tracked manually using tracker, which is subject to human error. So the conclusion, what does it mean? So why does the bottom part of the slinky remain stationary? The bottom of the slinky remains constant because the tension force from the top of the slinky equals the force of gravity until the top part of the slinky comes down. The slinky is said to be in a state of static equilibrium since the two forces cancel each other out to give 0 net force. And then what would happen if more weight was added to the bottom part of the slinky? I believe it would still behave the same despite the additional weight. The tension force would still equal the gravitational force. The only difference would be that the initial stretch before dropping the slinky would be larger according to Hooke's law, which states that the extension of the spring is proportional to the force applied on it. Thank you.